Okay, let me start. Am I audible? Hello.
Hello, sir.
Am I audible?
Yes, sir, you are audible.
Sir, you are well.
So last day we was discussing Carnot cycle. And I told you this is regarded as the basic thermodynamic cycle. Many thermodynamic relations actually can be interpreted or can be evaluated using this Carnot cycle. And also certain conclusions which we'll get from Carnot cycle, which are of utmost importance, particularly in regard to conversion of heat into work. Now, the last I told you from the ideal Carnot cycle, one gets the idea of another state function, which is the entropy function. Which is abbreviated by S. Now, how it is so? Let's see. In the PP diagram, as I told you, this is the step 1, then step 2, then step 3, and last step 4. A, B, C, D. These are the total 4 steps. Here, in step 2 and step 4, heat change equal to 0 as they are adiabatic process. In step 1, your reversible heat change, what was the expression? That is nR T1 ln V2 by V1. Similarly, in this third step, your reversible heat change was nR T2 ln V4 by V3. Final volume by initial volume. And if we rearrange it, then it was equal to minus nR T2 ln V3 by V4. And in place of V3 by V4, what we can put? That is V2 by V1 minus nR T2 ln V2 by V4. So now you can see, if I consider Q reversible 1, if I consider as a 1, divided by corresponding temperature T1, this is the corresponding temperature for this step, plus if we considered as Q reversible 2, that is reversible heat change in this third step, divided by the corresponding temperature. What is the corresponding temperature here? T2. Then what I will get? If I divide it with T1, then you will get nR ln V2 by V1. And if I divide it with T2, then I will get minus nR ln V2 by V1. That means it will be equal to 0. Hence, this whole thing, that is the summation for the whole cycle, the total heat change, reversible heat change divided by the corresponding temperature, that is equal to 0. That we are getting from this ideal Carnot cycle. Now we know for any state function x, any state function, what is the property of it? That means for a cyclic process, total change of that state function is equal to 0. If you compare this expression with this expression, then what you can infer? You can infer that this change in state function, that is equal to this one, that is dq reversible by t. And this is called, this x is actually called the entropy function, which is abbreviated as S. Hence, the small change in entropy, that is equal to the reversible heat change divided by corresponding temperature. And for a considerable amount of change, then delta S, it will be total heat reversible heat change divided by the corresponding temperature. So this is the expression of entropy change. That is the reversible heat change divided by corresponding temperature. And this concept we are getting from the ideal Carnot cycle treatment. Now consider a phase change. Phase change means suppose solid ice to liquid water. And we can consider it is an equilibrium process. Equilibrium, that is a reversible heat change is happening. What is the corresponding temperature? Corresponding temperature is the melting temperature, that is Tm. Now for this heat change, that is solid ice to liquid water, you require latent heat of fusion, and let that latent heat of fusion is given by Q fusion. This amount of heat is required. I think you can remember it is around 80 calorie per gram. Hence, for this reversible heat change, what is the corresponding entropy change? That is entropy change for the fusion process. That will be equal to corresponding latent heat of fusion divided by corresponding temperature, that is the melting temperature. Then if I tell what will be the entropy change of the solidification, this will be just the revert, that is negative of this, negative of Q fusion by Tm, that is negative of delta S fusion. Delta S solidification will be the negative of delta S fusion. Similarly, during evaporation, that is change of entropy during evaporation process, it will be Q evaporation, latent heat of evaporation, divided by the boiling temperature T. So these are the expressions of entropy change during phase change, and we consider phase change occurs under equilibrium condition.
Can you show the previous page? I will take a screenshot.
What?
Previous page, second page. I will take a screenshot.
This one?
Okay, sir. Done, sir. Thank you.
Okay. Now, what is the significance of this entropy change? You see, when solid ice to liquid water, this is happening. Delta S fusion, because this amount of heat is required, this is positive. You have to supply this amount of heat. Positive means system will absorb this amount of latent heat for this fusion process. And latent heat of fusion, it is a positive quantity. That is, entropy is increasing for this melting process or fusion process. Similarly, entropy of evaporation, this is also positive. That is, entropy is increasing for the evaporation process. Evaporation process means it is the liquid to vapor. This is the evaporation process. But if you consider solidification or liquefaction, that is the reverse of it. In those cases, delta S will be negative quantity. That is, entropy will decrease. From this, we may conclude that entropy, it is a measure of randomness of the system. Measure of randomness or disorderness of the system. Or disorderness of the system. Because when solid ice to liquid water or liquid water to vapor, For this phase transitions, ultimately randomness of the system is increasing. Solid ice, it is less random, less disordered. Liquid water, relatively more random or more disordered. Similarly, liquid to vapor, randomness or disorderedness increases. Hence, whenever entropy is increasing, it will correspond to increase in the disorderedness or randomness of the system. That's why it is regarded as the measure of the randomness or disorderedness of the system. And in thermodynamics, in your higher semester, when you will go through reversible the statistical thermodynamics, you will get one famous expression: S is equal to K ln W, where K, it is the Boltzmann constant, that is R by Na. R means ideal gas constant. Na, you know, Avogadro constant or Avogadro number. This ratio is the Boltzmann constant. In some books, it is given by K suffix B. And ln W, where W is the thermodynamic probability. Thermodynamic probability. That means entropy, it is a measure of thermodynamic probability, and thermodynamic probability is related with the randomness or disorderedness of the system. Thermodynamic probability means in how many intermediate steps you can rearrange a particular system. If there are more number of intermediate steps by which you can rearrange your system, it is called thermodynamic probability is high. And in that way, its randomness or disorderedness will also be high. That's why entropy, it is seen as a measure of randomness or disorderedness of the system. Now, I was talking about a reversible process. So let's say, let us examine it more details. Let us consider this type of closed environment. That is, heat is not passing through the system and the surrounding. This is liquid water. And there are some amount of solid ice is in equilibrium with the liquid water. So we can consider temperature as 0 degrees centigrade. Overall, your atmospheric pressure is 1 atmosphere. Under this condition, some amount of liquid water is in equilibrium. This is the equilibrium sign with solid ice. Now you know all type of equilibrium always are dynamic. Equilibrium is not static. Equilibrium is a dynamic. What does it mean? That means some amount of liquid water will be converted into solid ice, and some solid ice will be converted into liquid water under the equilibrium condition. This is the dynamic equilibrium. Now, when the liquid water will form some solid ice, that process, it is called solidification. Solidification. And when some solid ice will be converted into liquid water, that is called melting. And just right now, I have shown you that melting or fusion, that is entropy change during fusion process, that is equal to minus of entropy change of solidification. Hence, what is the total entropy change for this two-way process? That is entropy change for the total system plus surrounding. If I consider liquid water as system, then your solid ice will be surrounding, because I have considered as a closed environment. That means it is not interacting with anything else. there is only liquid water and solid ice which are in contact, and these two are interacting among themselves. There are nothing else with which this liquid water or solid ice will do an interaction. Hence, if I consider liquid water as a system, then your solid ice will be considered, you can consider it a surrounding or vice versa. You can consider liquid water as surrounding and solid ice will be considered as a system. In any way, what will be the total entropy change? That is the entropy change for the system plus entropy change of the surrounding. As these are equal with the negative sign, it will be equal to 0. So that's why we can say for a reversible or equilibrium process, entropy change of the universe, which is equal to entropy change of the system plus entropy change of the surrounding, that is equal to 0. For a reversible or equilibrium process, the total entropy change of the universe will be equal to 0. That is, entropy will remain constant. Entropy of what? Entropy of not system or not surrounding only. You have to consider the entropy change of the whole universe, that is system plus surrounding. That will be equal to 0 for a reversible or equilibrium process. What about for an irreversible or spontaneous process? Let's see.
Positive.
We are considering that's true, it is positive, but we have to explain it. Why? Let us consider two temperature regions. One is the source of heat. Another is the sink of heat. Source of heat, that means T1 is greater than T2. Now, one of the statement of second law, as I told you, that heat spontaneously or irreversibly transfers from a body at higher temperature to a body at lower temperature. If you want to convert heat from lower to higher, that is not spontaneous. You have to do some work. Otherwise, heat cannot be transferred from lower temperature to higher temperature. But heat always spontaneously moves from higher temperature system to lower temperature system. So here, this is at higher temperature, this is at lower temperature. So let us assume that Q amount of heat transfers spontaneously from this higher temperature source to lower temperature sink. Then what will be the entropy change of the source? Because Q amount of heat is released from the source, that means it will be minus Q by what is the corresponding temperature? Temperature is T1. This is the entropy change of the source. And what will be the entropy change of the sink? This Q amount of heat is going inside the sink spontaneously. That means sink is absorbing Q amount of heat. That means Q will be positive now. What is the corresponding temperature of the sink? That is T. Then what is the total? Delta S total. That is the delta S source plus sink. That is minus Q by T1 plus Q by T2. Hence, if you consider Q as common, then it will be equal to T1 minus T2 by T1. And as T1 is greater than T2, this is a positive quantity. Hence, for an irreversible or spontaneous process, the entropy change of the universe, here you can assume the source as the system and sink as the surrounding, or vice versa. I don't care. But overall, total entropy change, that is a positive quantity. Positive quantity means entropy of the universe will increase for any irreversible or spontaneous process. Just like your water flows spontaneously from higher altitude to lower altitude. It is a spontaneous process. And during that process, entropy of the universe is increasing. And as you know, all the natural processes occurring on the universe that is spontaneous in nature. That's why we can say that entropy of the universe is increasing. This is the another statement of second law of thermodynamics. Because in universe, whatever natural processes are happening, all the natural processes are irreversible or spontaneous. And as a result, the entropy of the universe is increasing. And if I draw the variation of entropy with progress of any process, suppose progress of any natural process, so this is negative, this is positive. The natural process, that means entropy will gradually increase from a negative value, it will gradually increase. And when, so this is all spontaneous because entropy is increasing. But when equilibrium comes, that is, suppose water is flowing from higher altitude to lower altitude. When the water comes at the level of sea, what will happen? You can consider as equilibrium has been established. So when that equilibrium has been established, effectively there will be no change of entropy. This is now the entropy change will be 0. So this is the variation of entropy with progress of any natural processes. And the second law of thermodynamics also tells you that entropy of the universe is increasing.
Sir, one doubt. Sir, why it starts from negative? Why not positive, sir?
If it is positive, then where it will go? It will increase and increase and increase. So can it reach a 0 value when equilibrium will be established?
Okay, sir. Okay, sir. Understood.
Entropy will increase from a negative value. And then if you consider the change of entropy, that entropy itself is meaningless. Change of entropy is only the meaningful quantity. The change of entropy is positive, okay? And when it reaches the equilibrium condition, effectively there is no change of entropy. Now, how the entropy changes with temperature or with volume and temperature or pressure? First, consider isothermal gas. And for simplicity, we are considering ideal gas. Isothermal process for ideal gas. What does it mean? There will be no change of internal energy. And hence Q will be equal to minus of W. From first law, Q will be equal to minus of W. Now, what is the expression of W for an isothermal change for ideal gas? Minus nRT ln V2 by V1. Hence, what will be the Q? Q will be equal to, it will be equal to nRT ln V2 by V. Reversible. Reversible isothermal process, ideal gas. What is the corresponding entropy change? Entropy change is the reversible heat change divided by corresponding temperature. Hence, in this case, the expression of entropy change will be N into R ln V2 by V. So in that way, your entropy will be dependent on volume. They are considered for ideal gas. So this is the NR ln V2 by V1. under isothermal condition, how entropy changes with change in volume. Now, if it changes from V2 by V1, we can write it nR ln P1 by P2. Because for ideal gas, V2 by V1 will be equal to P1 by P2 when temperature is constant. So this is the variation with either volume or pressure under isothermal condition for an ideal gas, change of entropy. Now suppose how entropy changes with temperature. So here again two cases. Consider volume constant. Then you know what is CV? CV is equal to dq by dt under constant volume condition. Hence, what is dq? dq is equal to Cv into dt under constant volume condition. Then what is the change in entropy? dq by t. That means it will be Cv dt by t. Now if you integrate, that is S1 to S2, if Cv is independent of temperature, it will come out of the integration sign. And what will be the case? Delta S will be equal to Cv. কত হবে? বলো, tell. What will be the integration of this?
ln T2 by T1.
ln T2 by
ln T2 by T1.
Okay. Similarly, if pressure remains constant, then delta S will be Cp ln T2 by. So this is the variation of entropy with temperature, either at constant volume case or at constant pressure case. Now, if both volume and temperature changes, then you have to add those two. That is nR ln V2 by V1 plus Cv or Cp, whatever it may be, ln V2 by. You have to add those. So this is the expression of entropy. Now, with all those
Sir,
expressions,
why to add? Can you explain once more why to add the two?
When both volume and temperature changes. When both volume and temperature changes, you have to add those two terms. Here one term, the first term corresponds to temperature constant process. The second term corresponds to constant volume process. But when both changes, you have to add those two terms. Okay, with all those expressions, now first let us consider some numerical analysis. Okay, let's see this one. This is from Carnot Cycle. An ideal heat engine operates between temperature T1 and T2, and we have given purposefully that T1 is greater than T2. That means in this particular case, T1 is the source, T2 is the sink. T1 is greater than T2. And part cycle Q2 is minus 4.5 into 10 to the power 6 calorie. In one cycle Q2, that means 2 indicates the sink and 1 indicates the source. Now Q2 is equal to minus 4.5 into 10 to the power 6 calorie. What does it mean? That means part cycle, this amount of heat is released in the sink. Heat release in the sink. The heat release, that's why it is the negative quantity. And where heat will be released? Heat will be released in the sink. So this amount of heat is
Sir,
released in the
Q2
sink
should
part
be
cycle.
positive now. Sir,
Huh?
Q2 should be positive because the sink will absorb the heat and the source will release the heat.
That's true. That's true. Here actually I have misplaced the Q1 and Q2, I think. Yes. Heat released to the sink. Heat released to the sink. It should be negative, no? Heat. No, 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 no. Heat released to the sink. What does it mean? That means sink is absorbing this amount of heat. So sink is absorbing this amount of heat. Just a moment, I have a call. Hello. এই যে ক্লাস নিচ্ছে হ্যাঁ 12টার পরে যাচ্ছে okay okay actually here I think the nomenclature from where I have got this the nomenclature are different. They use some other nomenclature, and here we are considering some other nomenclature for that is for positive and negative sign convention. Sign conventions are different. Then here also Q will be Q2 will be positive, delta S will be positive. Both will be positive. Anyway, so part cycle, that means ultimately whatever you have to consider that sink is absorbing this amount of heat and entropy change is this. Entropy change of the sink is this. These are given. Then T1, temperature of the source is 300 degrees centigrade. Calculate the efficiency of the engine and work done part cycle. So this is the problem you have to do. There's a efficiency calculation is rather straightforward because you know efficiency is the T1 minus T2 by T. T1 is given 300 degrees centigrade, that is 573 Kelvin, that is given. If you can calculate the temperature of the sink, that is the T2, then you can determine the efficiency of the engine. Now, how to determine the T2? For that, we know the delta S is equal to Q by T. And for the sink, the entropy change of the sink, that is where I am putting the value 2. That means it will be the heat change of the sink divided by the temperature of the sink. And both are positive quantity. Okay, you have to because we have used this convention. So hence, what will be the T2? T2 will be Q2 by delta S2. That means it will be this by this. And T2 will be 300 Kelvin. So when temperature of the sink is calculated from this expression, we can determine the efficiency of the cycle, and it will be around 48%. That is 0.48 or 48%. That means, what is the meaning of this? It means if 100 calorie of heat is absorbed from source, then 48 calorie will be converted into work, and rest amount, that is 62 calorie of heat, will be wasted. Just the meaning of 48% efficiency means is this. That's 48 if you absorb 100 calorie of heat from the source, 48 calorie of heat will be converted into work and 62 calorie of heat will be released to the sink.
It should be 52.
48% efficiency. Efficiency of what? Efficiency of conversion of heat into work. Hence, if the system absorbs 100 calorie of heat from the higher temperature source, it will convert 48%, that is 48 calorie into work, and the rest amount of heat, what is the rest amount? Sorry, the rest amount will be not 62, I think 52. The rest amount, that is 52 calorie of heat, it will be released to the lower temperature sink. So this is the meaning of 48% efficiency. Okay, now work done per cycle. In one cycle, what is the amount of work done? So what is the amount of work done? Amount of work done is the total heat absorbed from the higher temperature source into the efficiency. From the higher temperature source, what is the amount of heat the system is absorbing? If you multiply it by the efficiency, that is the work done. That means we have to determine Q1. If you don't determine Q1, that is the what is the amount of heat the system is absorbing from the higher temperature source, you cannot determine what is the amount of work. Again, how you can determine Q1? This relation, you know, the total entropy change for the whole cycle, that is equal to 0. That means Q1 by T1 plus Q2 by T2, that will be equal to 0. And from here, your Q1 will be equal to this. Actually, in our convention, it will be minus. So this amount of heat is absorbed. So this is the amount of heat the system will absorb from the higher temperature source. Then what is the work done per cycle? You have to take the mode of it. That is the amount of heat which is absorbing from the higher temperature source into the efficiency. And this is the amount of work done per cycle. So in that way, we can determine the work done per cycle. So very simply, if I tell you what is the efficiency of steam engine under normal atmospheric condition. In a steam engine, what is the temperature of the source? That is the steam. And under normal atmospheric condition, what is that is under 1 atmosphere? What is the temperature of steam? 100 degrees centigrade. That means 373. And what is the temperature of the sink here? Temperature of the sink will be the atmospheric temperature. If we consider 300 Kelvin as atmospheric temperature, divided by 373. So this is the maximum possible efficiency of an steam engine under normal condition. If you increase the pressure, then temperature of steam will be higher, and then efficiency will be slightly higher. But under normal atmospheric condition, this will be the efficiency, maximum efficiency of a steam engine.
Sir, one thing. Sir, can we say that Q1 equal to W plus Q2?
Q1 is equal to
W plus Q2.
Yes, you can.
Sir, then can't we say that Q1 will be equal to 4.5 into 10 to the power 6 into 100 by 48? Sir, because Q2 amount of heat
100
is
by 48 people. You don't know the W. In this problem, we don't have Q1, we don't have W.
Sir, but we know the efficiency. We know the efficiency.
Efficiency, we know efficiency, so that's why using that efficiency value, we have determined the W.
Sir, because efficiency is that thing only, no, that is W by Q1. How
That
much
means
amount of work can be done by the engine if
but
Q1
if you
apply,
don't know
Q1
Q1, if you don't know the Q1, then how you can use the efficiency value? Because efficiency
sir,
value will be
because we know.
efficiency value will be operative on Q1. First, we have to determine
Sir,
the
but
Q.
Acha. Sir, I thought that if we know Q2, then
Okay.
we can determine Q1 by
I
efficiency.
It is not possible. First, we have to determine the Q1 because efficiency means the amount of heat absorbed from the source into efficiency. That is the one. Okay, first, you have to determine what is the amount of heat the system is absorbing from the source. Okay, let us consider the second one. That is a problem with entropy change. 5 gram mole of water, initially at 27 degrees centigrade, are converted to a final state of water vapor at 227 degrees centigrade. 5 gram mole, that means how much amount of water? 5 into 18 gram. This amount of water, initially at 27 degrees centigrade, that means it is liquid water. And it is converted to a final state of water vapor at 227 degrees centigrade under 1 atmospheric condition. Assuming the vapor to behave ideally, calculate the total change in entropy. Given heat capacity of liquid water, 1 calorie per gram, heat capacity of water vapor, 0.4 calorie per gram, and latent heat of vaporization of water, 540 calorie per gram. These values are given. Anyway, can anyone tell me why these two values are different? Heat capacity of liquid water is 1 calorie per gram, and heat capacity of water vapor is 0.4 calorie per gram. Why it is less than half heat capacity of water vapor? Any idea?
Sir, I think because the water molecules are closely located, so to increase their temperature, it is difficult as there is more amount of intermolecular interaction.
Closely spaced is not scientific answer. Liquid water, they are intermolecularly hydrogen bonded. Now, if you want to increase the temperature by 1 degree, suppose you have taken 1 gram of liquid water and you want to increase the temperature by 1 degree, then you have to break those hydrogen bondings also. Not only you have to increase the temperature, that is the thermal movement. Temperature is a measure of thermal movement. But when you are increasing this thermal movement, you have to break the hydrogen bondings also. And to break those hydrogen bondings, you require some amount of energy. That's why for liquid energy, in order to increase 1 degree temperature, you require more heat. Whereas in case of water vapor, hydrogen bonding is practically absent. Hence, to increase the temperature by 1 degree, you require less amount of. Anyway, so here, to this problem, we have to see what are the corresponding initial steps, what are the final steps, what are the intermediate steps, and we have to determine the entropy change of all the intermediate steps, and then we have to add all those, sum up all those. So initially this is 5 gram mole, that is 90 gram of water at 300 Kelvin, 27 degrees centigrade means 300 Kelvin. And this is the final step, 90 gram of water vapor at 540 Kelvin. So obviously, from 300 Kelvin, that is 27 degrees centigrade, everything is under 1 atmosphere pressure. If pressure is 1 atmosphere, then at what temperature water will evaporate? At 100 degrees centigrade, that is 373 degrees Kelvin. Hence, the initial step will be conversion of liquid water from 27 degrees centigrade to 100 degrees centigrade. Now, this is liquid water at 1 atmosphere pressure and 100 degrees centigrade. Here, phase transition will happen, and you will get 90 gram water vapor at 373 Kelvin. Then we have to increase the temperature from 100 degrees centigrade to 273 centigrade, that is 540 Kelvin. So this is step 1. This is the phase transition step 2, and increase in temperature. This is also increase in temperature. This is also increase in temperature, and intermediate there is a phase transition. The volume, pressure is not changing. Now for step 1, this is an increase in temperature. So what is the expression? Delta S is equal to total heat capacity ln T2 by T1. This is the total heat capacity. Total heat capacity means if I consider specific heat capacity gram per calorie per gram, then you have to multiply with the amount in gram. That is the total heat capacity. That's why it is the 90 into 1. 90 gram into 1 calorie per gram. That is total 90 calorie. That is the total heat capacity. ln T2 by T1. T2 by T1, that is 370 Kelvin divided by 300. So this is the step 1. That is the entropy change for step 1. And to be particular, for entropy, the unit is because it is Q by T. That means calorie per Kelvin. This is the unit of entropy change. Now for step 2, it is the phase transition. And this is the total heat change during phase transition divided by the corresponding temperature. That means the total latent heat of evaporation. So 540 calorie per gram is the latent heat of vaporization. And what is the total amount of water? 90 gram. Hence, what is the total latent heat? 90 into 540. What is the boiling temperature? 373. So this is the delta S for step 2. Similarly, for step 3, again increase in temperature. Okay, this is not 540, it is 500. Okay, I think it is 273 Kelvin. No? This is 273. 273 means 500, not 540. So that's now the amount is 90, but heat capacity is 0.4 calorie per gram. And this is the total 90 gram. This is the total heat capacity for 90 gram of water vapor. ln 500 by 373. So this is the change in entropy for step 3. Hence, the total change of entropy. We have to add all the 3 steps, all the 2 intermediate steps.
Sir, one question.
Tell.
Sir, in step 1, sir, our pressure is constant, but sir, our temperature is changing. And we know, sir, PV equal to nRT. So, sir, volume will also change. So, sir, we'll not account that entropy change in.
We are not accounting here.
Sir, why?
Absolutely. That's for simplicity. Absolutely, it is for 100, that is 27 degrees centigrade liquid water volume, and 370, that is 100 degrees centigrade liquid water volume are not same. Obviously, it will increase. Yeah. But here, for simplicity, we are ignoring that. Nothing else. There is another problem in terms of entropy change. You will see it. You can do it by yourself. Okay. I will not discuss more today. The next, okay, this is the TS diagram. That is TS diagram for the ideal Carnot cycle. The y-axis is temperature and x-axis is the entropy. So this is the initial step. Now, first step is the isothermal expansion. Isothermal expansion, that is temperature will remain the same. That means it is a horizontal line. Temperature is not changing. And expansion process, that's why entropy will increase because randomness is increasing. That's why it will get this line. Second step, this is adiabatic, reversible adiabatic step. So reversible adiabatic step, that means Q reversible, it is 0. That's why delta S is equal to 0. There is no change of entropy. That's why it is vertical line. Entropy is not changing. And you know, in adiabatic expansion, temperature drops. That's why temperature is decreasing. Then isothermal compression, volume is decreasing. That means entropy is decreasing, randomness is decreasing. And last step is the adiabatic compression, reversible adiabatic compression. That means entropy will remain the same, temperature will increase. This is the variation for temperature and entropy for an ideal Carnot cycle. Okay, and just I forgot, if I consider both reversible and irreversible, if I combine, then it is greater than equal to 0. And this is called Clausius inequality. When delta S universe greater than 0, it will correspond to irreversible or spontaneous process. And when the entropy change is equal to 0, that is when there is no change of entropy of the universe, it corresponds to a reversible or equilibrium process. So in summary, if we combine these two conditions, that is called Clausius inequality. Next day, okay, when you all are returning, on which date?
6th.
6th means
Friday, sir. Next Friday.
Next Friday. So next Friday, tell me whether I will take online or offline. Because this
Sir,
Monday.
how could we do on that day, sir? We will be reaching there.
Yes,
Friday.
sir, it is not possible.
It's not possible, na?
Yes, sir, it will not be possible.
Okay, then no problem. Then I will take your offline class that next Monday. Okay. From that next
Okay, sir.
Monday, I will take your offline. And okay, then I will discuss in your class. I will. But in that week, I think you have your CA1. When you have your CA1?
Sir, it
Sir,
is
it is
not
not
decided.
decided. Teachers will decide when to
Teacher
take.
will decide.
Okay, go. Take it. We will inform you. Okay, next when I will meet you in your offline class, I will start the concept of Gibbs free energy. Today I am leaving. Okay, bye.